Good morning, everyone, and thank you for joining us today. In this discussion, we will explain what an API is, including its architectural evolution, protocols, and security mechanisms. All right, let's jump right in. Here's a quick roadmap of what we're covering. We'll start with a foundational analogy to get us all on the same page. Then we'll pop the hood and look at the technical mechanics, trace the really fascinating evolution of API architecture, see how they literally power the modern economy, and then wrap up with the absolutely crucial topic of security. So first up, let's talk about APIs as the digital mediator. To really get a gut feel for what an API does, we're going to start with a classic analogy that honestly just works perfectly. Imagine you're sitting in a restaurant. You have a menu, which is basically a list of what you're allowed to ask for. But you can't just barge into the kitchen and start grabbing ingredients, right? You need an intermediary, and that's the waiter. The waiter takes your specific order, goes to the kitchen, communicates your request, and then brings back exactly what you asked for. In this story, the API is the waiter. It's the clean, standardized interface that lets one piece of software, the client, get what it needs from another, the server, without either one having to know about the messy, complicated inner workings of the other. Okay, so let's translate that analogy into a more technical definition. An API is, for all intents and purposes, a formal contract. It's a precise set of rules and protocols that defines how software components are supposed to interact. And that word contract is key. It establishes a secure and predictable boundary, allowing developers to plug into another service's features or data without needing access to the source code. It's the foundation of modern software development. So now let's venture into that digital kitchen. What's really happening at a technical level? It all comes down to a fundamental process, the request and response cycle. This is the engine room of any API call. The speed and efficiency of that cycle really depends on the language or format being spoken. This table breaks it down perfectly. For a long time, XML was the standard, especially in big enterprise systems. But as you can see, it's really chatty. We call it verbose, and that creates a lot of CPU overhead. Then along came JSON, which was a game changer. It's lightweight, human-readable, and became the de facto standard for web and mobile APIs. But if you need absolute peak performance, maybe for communication between your own internal microservices, you'd use something like Google's protocol buffers. It's a binary format, which means it's incredibly compact and lightning fast to parse. Now, for any of that data to actually travel over a network, it has to be packaged up. Think about shipping a complicated model. You'd probably have to take it apart and put it in a box with instructions. That's marshalling. It's the process of taking a complex object living in an application's memory and converting it into a flat format like JSON or binary for sending. When it gets to the other side, the receiving system does the reverse. It reads the instructions and perfectly rebuilds the original object. That's unmarshalling. This whole process is absolutely fundamental for systems built in different languages to understand one another. So it's pretty clear that APIs haven't always looked the way they do today. They've gone through this constant, fascinating evolution, adapting to new technical challenges and demands. Let's actually trace that journey. This timeline really tells the story. We started back in the 80s with remote procedure calls, or RPC, which was mind-blowing at the time. You could run a function on a different machine. The 90s tried to standardize this with things like Corba, which was, well, it was incredibly complex and kind of collapsed under its own weight. The real turning point was in 2000 with the formalization of REST. It embraced the principles of the web itself, using standard HTTP, which made it simple, scalable, and stateless. And then in 2015, Facebook released GraphQL to tackle some of the data fetching inefficiencies that even REST couldn't solve. And this is the critical difference between the two modern giants. With a REST API, you request a resource. Let's say you ask for a user's profile. You get everything: their name, email, address, purchase history, the whole shebang. Even if you only needed their username. That's called overfetching. GraphQL flips the script entirely. The client doesn't ask for a fixed resource. It sends a precise query specifying exactly the fields it needs. Just give me the username and email, nothing else. This is an absolute game changer for mobile apps operating on slow or metered networks. But of course, there's no free lunch. The incredible flexibility of GraphQL introduces some new challenges, and a big one is called the N+1 query anomaly. This is a nasty little trap where a single innocent-looking GraphQL query, say, get me these 100 blog posts and their authors, can explode into 101 separate database queries on the back end. One query for the posts, and then one new query for each post's author. As you can imagine, this can absolutely crush a server. So how do you fight that N+1 beast? Well, thankfully, some very smart engineers came up with an elegant solution called the data loader pattern. You can think of it as a clever little optimization layer. Instead of letting all those individual requests hammer the database, it intercepts them. It collects or batches all the author IDs it needs to look up from that single GraphQL operation. Then it consolidates them into a single efficient database call. And as a bonus, it caches the results. So if you ask for the same author twice, it doesn't even have to go back to the database. It's a beautiful solution to a thorny problem. Okay, let's pull our heads out of the code for a minute and look at the bigger picture. Because APIs are so much more than just a technical implementation detail. They are, without exaggeration, a fundamental engine of the modern digital economy. I mean, just look at this number from the Harvard Business Review. 4 hours per employee per week. That's half a day just wasted toggling between different applications, copy and pasting data. API integrations directly attack this inefficiency. They allow our tools to talk to each other, bringing the data and functionality we need into the context where we're actually working. That's a massive productivity gain. Not all APIs are created equal, though. They're generally categorized by who can access them. You have your open or public APIs, which are out there for any developer to use and innovate with. Then you have partner APIs, which are shared only with specific strategic business partners. Most companies have a huge number of internal or private APIs, which are like the central nervous system connecting all their own services. And finally, there are composite APIs, which are really interesting. They act as aggregators, calling several other APIs behind the scenes to deliver a single, unified response. Now, this might sound a bit academic, but it gets to the heart of why APIs are so economically powerful. Endogenous growth theory basically says that real sustainable economic growth comes from innovation within the system. APIs are the perfect example. They allow a company to become a platform. They create building blocks that other companies can use to create entirely new products and services, driving innovation across the entire ecosystem without having to reinvent the wheel every single time. All right, but let's be realistic. Every time we open one of these powerful digital doorways, we also create a new potential point of entry for bad actors. APIs dramatically expand a company's attack surface, so securing them isn't an afterthought, it's priority number one. Let's wrap up by looking at how we do that. When we talk about web security, the Open Worldwide Application Security Project, or OWASP, is the authority. And one of the top threats they identify for APIs is Broken Object Level Authorization, or BOLA. It sounds complex, but the attack is terrifyingly simple. Imagine a URL that looks like API/document/123. A BOLA vulnerability is when an attacker can simply change that number to 124, and the server just hands over a document that doesn't belong to them. It means the system checked who the user was, but forgot to check if they were actually allowed to see that specific thing. It's a devastatingly common mistake. And that brings us to a point of confusion that's at the root of so many security flaws: the critical difference between authentication and authorization. Simply put, authentication is about proving who you are. Authorization is about defining what you're allowed to do. You absolutely have to get both right. And we have two industry standard protocols designed to solve these two distinct problems. First, you have OAuth 2.0. This is an authorization framework. When an app asks, "Can I have permission to access your photos?" That's OAuth 2.0 managing that consent. It grants access. Then, built on top of it, you have OpenID Connect, or OIDC. OIDC is the authentication layer. It's what verifies your identity, usually via login process, and gives you a token that proves you are who you say you are. They're designed to work hand in hand to create a secure ecosystem that handles both identity and permissions correctly. Phew, okay. We have covered a ton of ground. Let's just take a moment to pull it all together and summarize the most critical takeaways from our discussion. So let's recap. We established that APIs are essentially digital contracts. We looked under the hood at the mechanics of marshalling and unmarshalling data. We traced the architectural journey from the straightforward approach of REST to the hyper-efficient querying of GraphQL. We then connected all that technology to its massive impact on the economy. And finally, we highlighted why robust security, understanding the difference between OIDC for authentication and OAuth 2.0 for authorization, is absolutely non-negotiable. And I want to leave you with one final thought to chew on. So far, we've mostly talked about APIs as ways for applications to request data. But we are rapidly entering a new era of autonomous AI agents. And these agents will need APIs not just to read information, but to take actions in the world, to book flights, to send emails, to modify systems. How do we evolve our API designs to be secure, reliable, and auditable enough to serve as action execution frameworks for these autonomous agents? That, I think, is the next great frontier. Thank you so much for watching. If you enjoyed this, please subscribe, like, and share. And don't forget to hit the bell for more from Tech AI and beyond.